Last time we were looking at waves as moving energy, and we saw that we could classify waves further into how the particles move in relationship to how the wave is moving. And we try to restrict ourselves to looking at waves which require a medium. So one way to organize this information is by creating a flowchart. So let's take a look at that flowchart here. So waves as moving energy, we could say that they are mechanical waves or non-mechanical waves. And in grade 12, you're going to look at a non-mechanical wave as light. We're not going to deal with that in this particular course. We're going to look at mechanical waves, which are those waves that require a medium. So that's like a material. It requires a material to have the energy travel through it. Whereas non-mechanical waves, these don't have a medium that is required. And from mechanical waves, we saw that we can further classify waves based on how the energy moves in relationship to the particles that are being displaced. Because one way we look at the material is in which direction the particles are moving. So if they're moving along the wave or perpendicular to the wave. So these two can be classified as longitudinal or transverse. And for transverse waves, the easiest example to keep in mind is going to be we have a string. The string is tied on one end, and let's say you create one up and down motion. So we create the pulse, and we say that the pulse travels to the right, which is the wave, which is the traveling energy. So let's call this energy flow. And the particles, they're being displaced up and down. And when you have this scenario where the energy flow, aka wave, travels to the right, but the displacement is up and down, this is a transverse wave. And then for longitudinal, the easiest one that we're going to consider in this course is going to be a slinky laid out on the floor. And suppose that you push the slinky to the right, which means the wave is going to travel to the right as well. When this occurs, we classify this as a longitudinal wave. So again, the wave moves to the right, and then the particles are moving to the right as well for that displacement. But keep in mind that the displacement of these rings, they don't start from one end and they don't get carried with the wave. So the particles are only moving right, but when the wave finishes passing through it, the particles go back towards the left. So the displacement goes back to the left. So that's why I put in dashed lines that left motion. So this was true for the wave traveling through the string as well. So we saw it was going up, but then it also goes down. Now this is particular of the mediums that we're dealing with. The medium needs to require a force that's a restoring force. This restoring force brings back the medium into equilibrium. So what I'm trying to draw in dashed green lines here is the equilibrium line, so where the slinky was originally or where the string was originally. So the requirement that we're going to have in the medium is that it has a restoring force, which just means that the particles, once they are displaced, they want to go back towards the equilibrium line. So the medium needs a restoring force that makes the particles return to equilibrium once the wave passes through. An example of this restoring force is going to be the spring force or the tension force. And now going back into my discussion about longitudinal waves, I got a bit carried away there. The wave was moving to the right, the displacement goes to the right or to the left. In other words, it is parallel to the wave. And with our mechanical waves, we do have a third type, and the name is not a very creative name by any means. So we have transverse, longitudinal, and the third one is called complex waves. Complex waves, all they are is just a combination of longitudinal and transverse. So some examples of this type of waves is the most common wave that you think about when you think about waves, which is water waves. Now, I'm not going to get too much into discussion of complex waves. You could look into other videos for that. For now, I'm just going to introduce it to you. The other type that we see a complex wave occur is whenever you punch someone in the face, so like a UFC match that just occurred with Khabib, we have that when the fist hits the face, the energy travels along the surface of the skin. So in this case, we have a transverse wave, but the impact is also felt in towards the center of the head. So we have a combination of longitudinal, which occurs along the face, along the skin, and going into the face, which would be transverse waves. So this will be a punch to the face. Now in this lesson, I'm going to go further into longitudinal waves, and I'm going to look at another example which is more commonly used as sound waves. But before that, I want to first define the key areas of a longitudinal wave. So let's try to draw our slinky once again. And again, looking at the longitudinal waves, we have a slinky stretched on the floor. We push it to the right, so the wave will be traveling to the right. But the displacement of each individual ring will be going right and left. As the wave passes through, it will go to the right. Once it's finished passing through the slinky ring, the restoring force, which would be the spring force, brings it back to equilibrium, which is why it moves to the left. But notice that in this drawing, there's regions of space where the rings are more closely bunched together, and there's regions of space where the rings are further separated apart. We're going to put these two and give them specific names. So where the rings are grouped together more closely, we're going to call this areas of compression. And where the rings are further apart, we call this areas of rarefaction. So the name compression is pretty straightforward, right? Because that's when the rings are compressed together more, which means they're grouped more closely together. So they are compressed. But rarefaction, in political terms, faction is a group that's usually small, and rare means this is a rare, so it's not commonly occurring. So one way you can remember this is a not commonly occurring group, which in this case means that we are not very likely to find the rings grouped together, which is why in this diagram the rings are further apart. Think about the Hunger Games, right? The factions, all the different factions, which are all the different groups, and then rarefaction will be a rare group. So along this wave pulse, we see that it keeps on alternating between areas of compression and areas of rarefaction. So this is common for longitudinal type of waves. And this is a slinky. But since another example is sound waves, we're going to look at how longitudinal waves holds true for particles in the air. So as we suspect, we're going to have areas of compression and rarefaction, and since we're dealing with air particles and they're constantly always moving, but now we're going to look at regions of space. So in regions of space where they're compressed, the particles will be closer to each other, and where they're rarefacted or rarefaction, the particles will be separated more apart. So let's see if we can get a diagram of this. So again, we're dealing with sound waves, and in this case you can suppose that maybe something made a sound, which is on sound could travel in any material really, so it could be solid, liquid, or gas. But for the most simplistic case, you can just imagine the air particles. So here we have a little chick, and the chick sends out some energy due to its mouth through its beak, and that's going to send out energy through the air particles, which is going to make them move through regions of compression and rarefaction. So now we can label those. So as we mentioned, compression is where the particles are closely grouped together, and rarefaction will be where they're further separated apart. So you're not commonly going to find particles in a rarefaction region. So this is if we're considering the particles in the air. But another representation of longitudinal waves, and particular sound waves, is by measuring the pressure differences in the air. So that was looking at particles in the air. Now let's look at the pressure differences in the air. Now, why would we want to look at pressure differences instead of the number of particles in the air? Well, it is really hard to actually measure the number of particles. But with pressure, we could use instruments to do this. So it is much easier to look at the pressure differences in the air than the number of particles in the air. But looking at the particles in the air, we can look at pressure and the connection between the two. So as you might suspect, areas of rarefaction, where the particles are further separated apart, we're going to have lower pressure. And areas of compression, where the particles are closer together, we're going to have higher pressure. Now, to try to convince you further, let's first recall the formula for pressure and come back to this. Pressure is given by the force over the area. So if we make the area small, and the force is going to be higher because there's more collisions, which is the area of compression that we're considering, right? So in the area of compression, high force, low A, this results in a high pressure. You could put in some values to double check, right? And there is a rarefaction. We have a low pressure over a higher area. This would be low pressure. So you see how we could verify our number of particles by looking at pressure instead, because measuring pressure is easier than the number of particles. Now, normally the way it's represented is with darker colors and lighter color. I mean, a dark shade and a light shade for high pressure and low pressure, but that's hard on the iPad. So one way that I did that is by drawing more lines in a region to show high pressure and fewer lines in a region to show low pressure. Alright, so looking back at what we did, again, waves are moving energy. We can have non-mechanical or mechanical waves. So mechanical waves require a medium, and we have three types: transverse, longitudinal, or complex. And we determine which it is by looking at how the energy flow and its direction of the displacement of the particles in the medium. So if it's perpendicular, it's transverse. If they're parallel, longitudinal. And if it's a combination of the two, we call it a complex. One key feature that we talked about the medium itself is that it needs to have a restoring force, which brings the displaced particles back towards equilibrium. Looking at longitudinal, we have areas where we have fewer particles and areas where we have more particles. So for high particles, it's compression. For low particles is the rarefaction, so not commonly found groups, rarefaction. And sound waves is an example of longitudinal waves, so you could imagine as the particles in the air due to our little chick, or because it is harder to measure the number of particles and easier to measure the pressure, we could look at the pressure differences in the air instead. So low pressure will be rarefaction, high pressure will be compression areas, as we saw by looking at the formula for pressure.